What is the best type of wingtip configuration for VTOL drones? I don't know, but that is what we're going to find out in this podcast, amigos. We're going to look at a bunch of different wingtips, from the conventional like winglet wingtip to raked to just a plain wing terminating at the wingtip. But this is in the context of VTOL drones, which means that the drones take off vertically and land vertically. And this is a little unusual because most drones these days don't have wings, but that limits the speed of the top speed of these drones, because once you go faster than a certain speed, the rotors that rotate around start to break the sound barrier, and that slows down the aircraft. So if you want to go faster, you then have to start to adopt a more of an airplane configuration, which means that you do need wings, and as such, the wingtips automatically become very important parts of the craft as they are on a regular airplane. And to look into which of these wingtips is best, we're going to look at a paper called Aerodynamic Optimization of a VTOL Drone Using Winglets. Now, this is called a micro article, which is the first time I've come across such a thing, and I can say that it might be small on size, but not on impact. And I just made that catchphrase up, so I think Elsevier, the publisher here, should use it and pay me royalties. Anyway, we are in for a treat, because we are not only going to cover different wingtips designed for VTOL drones, but also we'll go through a couple different simulation methods. So the first way is the one that we're all used to, the CFD Navier Stokes approach. It's a very good method when it's done properly, and which is, I guess, the case for every method. But we're also looking at another method called Vortex Lattice method, VLM, or panel method is also another name for it. So this term might seem similar to one that is called lattice Boltzmann method, and we've done some podcasts on those. But they are different. They're not really related at all, actually. And so I'm going to quickly explain what a vortex lattice method is, because I personally quite like them, and I've even used them quite a long time ago when I was growing the best geometry from a genetic algorithm. So I'll talk about more about that once I covered vortex lattice methods first. So let's talk about that first. So the vortex lattice method is a potential flow solver. That means that viscosity is not present. As such, in its purest form, the vortex lattice method can't handle flow separation. It can't handle boundary layers. It can't handle anything to do with viscosity. But if you start to add outside information or a viscous coupler, it can. And in other words, you have to have other additional equations to take into account this viscosity. And the way it works is that you have your geometry, let's say a wing here, which they have here as well. And then you model this wing as a sheet of vortices. And if you don't know about vortices or the Kutta-Joukowski theorem, for example, or a vortex sheet, check out a YouTube channel, check out a YouTube video on our channel called Aero Fundamentals number 14, using vortex theory to calculate the lift of an airfoil. That will give you a good idea about what these things are. But by knowing the circulation and vortex distribution along this geometry, this wing for example, you can calculate the lift and the induced drag. But you cannot calculate any other viscous parts, such as I mentioned, the boundary layer, skin friction drag, pressure drag, etc. So that's the limitation of this particular method. But the major benefit of this vortex lattice method is that it's very quick, like really quick compared to regular Navier Stokes CFD. And that is actually why I used this method when I was growing the optimal solution for a wing shape given the specific geometric constraints. So my goal was to see what wing geometry would yield the lowest induced drag and the best lift induced drag ratio as well, because that's also important. That's also an indication of how efficient the wing is. So I decided to use a genetic algorithm, which is actually very simple. It might sound complicated, but I personally learned about it, then coded it, then ran it all within about 3 days. So it's actually quite easy to understand and do once you just get up and going. So essentially what it is you start off with a sample space, whether that is 5, 10, 50, 1,000 specimens, whatever. Then you grade each of these specimens and base this on certain characteristics that you want. And then from this initial specimen, like sample space that you graded, you then take the best samples, like the best grades, then let them breed to the next generation and add in some mutations and some crossbreeding, etc. And that is the crux of it. So you can change these things to ensure that your solution doesn't converge to one solution prematurely by increasing the chances of mutation or of certain parameters, or by making the grading system you use, which is called the fitness function, prioritize genes that are different on the fly. But there's a bunch of things that you can change, but the general crux of it is that simple. So say you have selected, let's say, 5 specimens to breed some of the next generation. The next specimens that you select could then be something very different by simply valuing difference more than any other quantity, including the lift or lift to induced drag ratio, or lift or induced drag, or whatever. And genetic algorithms are a very powerful tool to optimize a solution, but it takes a lot of specimens. So what that means for aerodynamics is that, say you want to find what wing geometry gives you the best lift-to-induced drag ratio, you need to then do lots of CFD or wind tunnel experiments, and that takes a lot of time and money, and to the point where you can't really do it. It's not feasible, practically speaking. So I mean, for example, the genetic algorithm that I use to calculate the lift and induced drag of something like 10,000 specimens. So imagine doing 10,000 simulations in CFD or 10,000 wind tunnel tests. You'd be there until kingdom come. It's not really possible. And that is where something like the Vortex lattice method comes into it. Because it is way quicker than Navier Stokes CFD and lattice-Boltzmann CFD, you can do 10,000 simulations quite comfortably. The question then becomes, well, how accurate is this lattice-Boltzmann method then? Sorry, this Vortex lattice method, not lattice-Boltzmann, Vortex lattice method. That's similar. I sometimes get confused with the names too. So it's likely that it isn't as accurate as the CFD, but it is the best option for doing genetic algorithms and doing a lot of simulations. So another possibility is using something called the Prandtl lifting line theory, which is similar to the Vortex lattice method in that it's inviscid, but in its purest form, it can't handle non-planar surfaces. And if you don't know what a non-planar surface is, listen to our podcast from a couple of weeks ago, podcast 167, where we cover what these geometries are. And so, but apart from that, the Prandtl lifting line theory is still very powerful, and it's a really great initial step as well. Not as good as the Vortex lattice method though. So with some outside information, this lifting line theory can kind of handle these non-planar surfaces, but it's still quite dodgy, and that's where this Vortex lattice method comes into it. So it's the next step up. So to determine whether the Vortex lattice method is any good for the modern day, considering that these things have progressed a lot since its inception, these researchers are also looking at how the results from these Vortex lattice simulations compared to Navier Stokes CFD simulations as well. So we'll be looking at that in our podcast as well. So let's get started. Let's get started at not only the wingtips, but also different methods as well. And that's quite a lot for such a micro article, sorry. So this paper ties into a podcast we did a couple of months ago that looked at how canting the wingtip changes the aerodynamics of a wing. And that was a pretty good podcast as well. And in this one, we're going to be looking at something similar to that as well, not just canting, but also sweep angle and taper ratio. So these researchers did this parametric study of the sweep angle for a raked wing tip, and also the taper ratio, which is how much the wingtip is pinched at the ends of the wing. So like, for example, if you say a wing has a taper ratio of 0.5, it means that when you go from the wing root to the wingtip now has a chord. It's only half that of the wing root. And they're saying here the taper ratio of the actual wingtip bit, so the start of the wingtip compared to the final bit of the wingtip. So in table 1, we see the raked wingtip, and 1 with a greater taper ratio means that the end of the wingtip has a much shorter chord than at the start. And as I mentioned, in addition to that, they're also looking at different cant angles, as we will cover. So this study was carried out with OpenFOAM, which is completely free Navier Stokes CFD software, and it's really good. It's like as good as commercial softwares, and like commercial softwares you have to pay like $50,000 per year to use it. OpenFOAM, completely free. So that's pretty nice. And we actually have a course on how to use it. So that takes you all the way from the very start, including how to even install it, to running your own DES simulations. So that's pretty good. And if you want to learn OpenFOAM, check that course out and link below. But anyway, in this study, they did a mesh convergence study, which is very impressive considering that this is only a 3-page paper. It's a micro article. And as we covered, it might be small on size, but not on impact. So that is impressive because we often come across like 20-page papers that don't even have mesh convergence studies. So that's pretty good on this paper, but I'm a little confused by their approach still. So they kind of had like 2 parts to this study. The first part, these are given in table 2 and 3. So the first part is in table 2, where they say it's called a mesh independent study. And in this table, they give 4 different mesh finenesses. And we can see that the lift and drag coefficients was stable pretty much at all 4 meshes here. So let me zoom in actually so we can see a bit better. So we have mesh M1, M2, M3, and 4. Then we have the different number of elements going from about 7.9 million to 25.1 million. And then the changes in the lift and drag coefficients based on the initial courses grid. And then from then on, the one before that. So that's this mesh independent study. But then in table 3, they present a refinement study for the wake and around the vortex region. So they have this picture below, which is the refinement in the wake and the vortex region. So I don't really get what this is, because in table 2, you found that the mesh independent study for the entire domain was good. Then why are you doing further refinement? I don't get it. So something else that is interesting is that even though in table 2 we see, let me zoom in again, even in table 2 we see that for the coarsest mesh, which is 7.9 million, the lift and drag coefficients are pretty much the same as the finest mesh, which was 25.1 million. So, and the two meshes in between at 12.3 million and 17.5 million give very similar results as well. So what I would have concluded is that you'd go for the 7.9 million cell mesh because that is giving you the same results as any of the other meshes, but you save like 10 million cells. So instead they chose to go for the second finest mesh, which had a 17.5 million cell mesh, which for some reason, I don't know why. And who knows, maybe there was a good reason, but due to the microness of this micro article, they left it out. I doubt it because they still had some room on the third page down at the end here. So I don't know why they would have left the information out, but they did. And as we've covered already, this paper is micro in size, but not in impact. And full disclosure, I really want that to be true because if it isn't, then the catchphrase I come up with that I'm sure Elsevier will want to pick up and use won't be true, which means that they probably won't pick it up and I won't get my royalties. And I really want to be a royalty baron or a sugar baron or some kind of baron because I seem to wear a lot of overcoats and I really like that look. But anyway, after they chose a 17.5 million cell mesh for some reason, they then started to refine the wake and the vortex regions to see how that affected the lift and drag coefficients. Now the refinements didn't seem to make much of a difference. I mean, the differences are like 0.1% in the lift and drag coefficients, which are probably well within the uncertainty of the CFD study anyway. So again, the coarsest mesh was good, but yet they chose to run with the finest mesh, this M3.4, which is 25.6 million cells in total. So I don't really know what's going on here. It's kind of like I'm watching Eurovision. I don't know what's going on, but I'm just enjoying the pretty pictures. I mean, it's not bad for the accuracy of this study because they've shown that increasing the number of cells doesn't make much of a difference to the lift and drag coefficients. But by using so many more cells, they just made it harder on themselves, unless this is kind of like a weird CFD flex where they want to show off how many cells they can use and even double or triple what they need, but they don't care because they have so many cells to waste. But anyway, there is one final part to the CFD setup, which is the validation. Now, they say that their procedure was validated with experimental data with a similar wing. That is a little concerning because, first of all, they don't seem to give any figures on that, so no numbers. I have no idea whether the CFD was in the 1%, 5%, 10% of the experimental data. That's up in the air. But also, they say that the experimental data came from a similar wing, but not the same. That is obviously not good, but that is what they said. So the validation process is not ideal, I'd say here at least, with what they've reported. But I want it to be known that this could happen for any paper, or even a regular size paper, or even an extended paper, not just the micro paper. And the microness of this paper did not influence this dodgy part of the study. Anyway, the researchers used the Spallett-Almaras turbulence model in RANs, not URANs, but just regular RANs. And the Reynolds number was 183,000. So the wing was also a NACA 0012 airfoil with an aspect ratio of 8. Now with all that information, I think that the Spallett-Almaras turbulence model was not quite adequate here because now that we are in that zone of transitioning to turbulence, that is a very difficult zone to be in. And if you don't believe me, well, first of all, I had the fortune or misfortune, however you look at it, of having to do some CFD on wings around this Reynolds number during my PhD with URANs, and that wasn't fun. It took ages to get anything even remotely accurate. But also, try it yourself and get an airfoil, then run it with these conditions, but at laminar, transitional, and turbulence Reynolds numbers, and just see how different the results become and compare them to literature. It is quite difficult to do CFD at this Reynolds number, and the Spallett-Almaras turbulence model is not really adequate, generally speaking. So I think that the CFD suffered because of this choice of turbulence model. And overall, I'd probably rate this CFD, let's say about 6 to 7 out of 10, 6.5. It's pretty good that they've got this mesh independent study. I don't really understand what they've done here, but at the very least, we know that the grid is fine. The validation could be better, and the turbulence model could be better. So that's probably about 6.5 out of 10, let's say. So anyway, they simulated these wings at 7 angles of attack, 0 degrees, 3, 4, 6, 9, 12, and 15, which takes us through the range of like low angles of attack up to about stalling and even into the stalling range a little bit. So first of all, let's look at the results in table 1. Let's zoom in here. Here we go. Nice and cozy. So This is the results of the induced drag of the wing with raked wingtips, and that's when you pull the wings back, like so they're pulled back a little bit, and they have different amounts of sweep and taper ratios. And just to refresh your mind, in figure 1 we do see this raked wingtip just here. That's what it looks like there. This is the leading edge up here and the trailing edge at the back. And the sweep refers to how much it is pulled back. So while the taper tells us effectively how quickly it is shrinking towards the wingtip, the sweep tells us how much this is being pulled back. And we see from table 1 that generally speaking, the sweeping of the wingtip more, regardless of the taper ratio, always increases the induced drag. So here we see increasing the induced drag, increasing the taper rate, increasing the sweep angle, increasing the induced drag, etc. And that kind of makes sense because typically when you sweep a wing, more lift is produced at the wingtip, which results in greater induced drag. Now, it seems like the greater the taper ratio though, the more the induced drag is produced as well. Now that is a little interesting because a greater taper ratio is usually beneficial for induced drag, but here we see kind of the opposite thing happening. And there are two reasons that I can think of why we'd be getting this trend here instead of the other trend that we expect, which is when you increase the taper ratio, the induced drag drops as you go to the wingtip. And that is the first reason that I can think of is that the CFD isn't accurate enough at here, and the small increases of a few percent are overshadowed by the uncertainty in the CFD. That is one possibility and a good one in my opinion. The second possibility is that if we look at figure 1, we see that the taper starts very abruptly. So usually there should be like a smooth transition, but here it's just a point at the leading edge that just starts and it's quite sharp. So I wonder if that negatively affected the induced drag. Maybe it even encouraged a vortex here to form because the flow might be coming over the leading edge of the wingtip section. I don't know, but I'm just curious because it is very sharp here at this point, so that might happen. Now in figure 2, we also see the effects of the winglet cant angle and height of the winglet on the induced drag and total drag, and this is cool. So the graphs show that let me zoom out a little bit here as well. So the graphs show that as the winglet increases in height, the winglet becomes taller, in other words, the induced drag drops as the total drag. And that makes sense because the taller the winglet is, the harder it is for the air to bleed around and create the vortex. So in other words, the greater the disconnect between the lower and upper surfaces, which is always beneficial for the induced drag, that's what happens. So that's what this bigger winglet is doing. Also, as the cant angle increases, the induced drag and total drag also drop, which also makes sense because the winglet would act more and more like a barrier as you put it up. So that all makes sense. So from this section, we can conclude that sweeping a raked wingtip more results in more induced drag, but I think that is more from this design than in general, where the wingtip is very sharply started, or maybe even in CFD inaccuracies. We can also conclude that increasing the taper ratio also increases the induced drag, which does not agree with general wing theory. It should be the opposite way. And this may also be because the sharpness of the start of the wingtip or the inaccuracy of the CFD. But some things that do make sense, a lot of sense, is that increasing the height of the winglet definitely reduces the induced drag and even the total drag. It also makes a lot of sense that canting the winglet more vertically makes it produce less induced and total drags. So that is the general geometry. Let's move on to the comparison between Navier Stokes CFD simulations and Vortex panel method simulations. So in figure 4, which is down here, here we go, they give a graph of the lift versus drag production. So let's zoom out a little bit here and so we can see better. Okay, so now they did make an attempt to calculate the viscous drag part of the wing with the vortex panel method, and this is inherently erroneous because listen to the description of how they did it. They said, first an overestimation of viscous drag of 4% and an underestimation of total drag was noticed. This is because the vortex lattice method is linear, that implemented a inviscid flow assumption, so that is true. They also say that the calculation of the 3D viscous drag is based on the interpolation of 2D parasite drag from the local wing lift. So there are quite a lot of problems with this approach. So the most glaring to me is that they use 2D results to calculate the 3D results. That is almost never a good idea because once you start approaching the wingtip, depending on the strength of the wingtip vortex, the flows wash down more here, which reduces the effective angle of attack on the wing here. And that's because the flow is more aligned with the wing, so the lift production drops here anyway. So the drag produced here is more like what is produced on the wing, 2D wing, at a lower geometric angle of attack. So I guess you could factor that in. which they might have done, but they also say that the 3D viscous drag is interpolated based on the local wing lift. But then they say that it is a linear function of the angle of attack, which also isn't strictly true, especially if you factor in things like separation and laminar separation bubbles. So I think this is a little problematic, this general approach to calculating the viscous drag part. But as a general approach, I guess that's just a good ballpark idea, I guess, but not to be taken like very accurately. But anyway, they also say that the parasite drag, which actually isn't constant with angle of attack, is used, and this is just an approximation. And also, the parasite drag is a term that is used somewhat vaguely. So some use it as the drag as zero lift, and they say that it stays constant throughout the lift, like the angle of attack range, which isn't true. Others use it just as the drag that is not associated with lift production. However, the production of lift affects the parasite drag anyway, which means that the definition becomes quite murky anyway. So that's a little bit of a gray area. Anyway, considering that the vortex panel method isn't meant to be the be-all and end-all, but rather a good first approximation, I think it's pretty decent to have these mismatches, but still get to within about 4% of the viscous drag calculated from the CFD is a pretty good job. Now, interestingly, they say that the vortex panel method underestimates the induced drag by 20%, which is because of the software XFLR5. So that's the panel method software, and this models the wake as a straight extension of the flat panels, which results in the overestimation of the lift and vortex drag. So what does this mean? First of all, I must say this last part is very insightful, and only those who have used panel methods and have good experience with them know what this is and can figure this out. So what they are saying is that the wake coming off of the trailing edge just extends straight back instead of down, and even slightly curved as you reach the wingtip, which happens in real life. So this inaccuracy in the wake production means that the induced drag won't be calculated accurately, nor will the lift completely. Also, the vortex strength, I think they were referring to the wingtip vortex, which makes sense because given the undeformed wake, which the panel method produces, that will also give errors in the induced drag, whereas in the real life, this vortex at the side actually sort of warps the wake a little bit as well, and that changes the drag. So it's very clever of them to have figured this out. Not everyone really talks about this kind of stuff, and it's actually quite rare to hear. So I quite enjoy this explanation. So they say that despite these trends, the CFD and XFLR5 gave the same general trends. So let's look at that. So in figure 4, we see that the three wings tested, the baseline, raked wingtip, and winglet wing, followed the trends quite well when it came to the overall drag. For example, the CFD showed that the baseline wing produced the most drag, which is the blue, like dark blue dash line, which the panel method also showed with the like the browny orangey star. The CFD also showed generally that the winglet wingtip produced the least amount of drag compared to less drag than the raked wing. The panel method kind of showed that as well, but marginally. So in table 4, we get some more numbers to compare them more quantitatively. And now actually I should mention that I don't know what the angle of attack is for this table. I don't think they mention it. But anyway, the CFD showed that for the induced drag of the winglet, it was better than the raked wing, which was better than the baseline wing. And this trend also held true for the panel method, but the difference between the raked wingtip and the winglet wingtip induced drags was marginal, whereas for the CFD, the Navier Stokes CFD, that difference was much greater. So that's one difference in terms of the overall results, but the trend still held quite consistently. Now, the total drag is interesting because, again, while the CFD and panel methods both show the same general trend that the baseline is the worst, the baseline wing, the raked wing is better than the winglet, and the CFD showed much greater drops in the drag for the two different wing tip designs compared to the baseline wing. So regardless of which wingtip you take, both of them are much better than the baseline drag. So from this, we can conclude that the panel method was pretty good. I mean, I wouldn't use it to give the final answer, but to get a general idea of the trends, it was very decent here. So if you look at from all this data, and if you want to then look at hundreds, thousands, or even tens of thousands of configurations, the panel method is the best approach in my opinion. And that's because it is giving us pretty good results and quite quickly. It's very cheap. And with that, we come to the end of our podcast. I really liked it because we saw it in a micro article. Some saw some interesting trends regarding raked wingtip designs and panel methods, which we haven't covered before. So I should say that if you want to get better at CFD, also check out our courses link in the description below. And if you aren't measuring the density of air in your experiments, make sure to do that, because you can easily introduce a 1 to 2% error in your results. And to get rid of that, we make an instrument called the Atmosphere Hawk, which can very accurately measure the density of air. You can find that in the link below. And with that, make sure to hit the like button and the subscribe or follow button. And I'll see you next one. Peace out, amigos.